We are talking about the expectation maximization algorithm. Two steps, the E step, the expectation step, and the M step, the maximization step. And we've already gone through the E step where we assign each data point a probability of belonging to model 1 or model 2. And let me just remind you that we're going to go ahead and assume we know the model parameters. How? We'll talk about that later on, but it's just like k-means. We're going to guess them to begin with. And we're going to compute the probability that each data point x sub I, y sub I, each data point in here, not just the red ones and just the green ones, every single one belongs to each model. So now at the end of the E step, we have associated with every data point two numbers. The probability you belong to model 1, the probability you belong to model 2. And now our job is to re-estimate the model parameters for each model, k equals 1 and 2, using the probabilities of model assignment. Let's assume we didn't have probabilities. If we were doing k-means, what would we have? We would say this point belongs to model 1 because it's closest to it. This point belongs to model 2 because it's closest to it. And what could we do to re-estimate the parameters of the line? Least squares, total least squares. Right? That would have been perfectly fine. But that's not really what we have. We haven't actually clustered the data in any real way yet. Every data point says, look, I belong to model 1 with this probability, I belong to model 2 with this probability, and now your job is to re-estimate model 1 and model 2. And so what do I have associated with every data point and each model is a probability, a weight that says, here's how likely I think I am to be associated with this model. Well, that's sounding really familiar. That's sounding an awful lot like weighted least squares, where we're going to use all of the data points to re-estimate model 1. We're going to use all of the data points to estimate model 2, but for model 1, we're going to use the weights associated with model 1, and for model 2, we're going to use the weights associated with model 2 that were computed for us in the E step. All right, now, it's always good to refresh our memory on how these things work. So let's drive through the weighted least squares all over again to remind ourselves how these techniques work. I'm going to establish again a quadratic error function in the model parameter, slope, intercept for model k. That's the superscript where k equals 1 or 2. It's the sum over all data points, I equals 1 to n, not just the red ones and just the green ones, where I'm going to multiply the residual, so this is a sub k xi plus b sub k minus yi, that's the vertical distance or the residual. I'm going to multiply that by the probability, which I'll now denote as w sub I, that's the ith data point, sup k, which is the kth model, and of course all of that gets squared because I want a quadratic error function. So this is weighted least squares. In fact, this is weighted least squares on a line, which we've already done. All right, let's just turn the crank here. It's a good exercise to remind ourselves how this works. Let's set this up in the linear algebra framework. I'm going to denote m sup k as my vector of unknowns. That's the slope and the intercept, which is this little 2 by 1 vector right here. Let's work on the inside now. So what multiplies the a is the x component. What multiplies the b is 1. That's the slope. And then, of course, that's minus the ith point. So this thing right here computes that vector of delta or residuals. And then, of course, we're going to compute the sum of the square of all of those. But before we do that, we're going to weight everything using this diagonal matrix, where the diagonal here are the probabilities associated with every data point, 1 to n, for the kth model. Okay, so now we've got our quadratic weighted error function. And now let's just turn the crank. So the error function is now the weighting matrix, which I'll denote as W with a K to remind ourselves that this is indexed on the model. And then I've got my data matrix. Notice that's not indexed on the model. It's just all the data. I've got my kth model, and then I've got my Y vector also not indexed on the model because we're using all of our data. All right, let's just go ahead and solve this equation. We know what to do. We're going to differentiate set equal to 0 and solve for the unknown m sub k. All right, the derivative is pretty easy. The 2 comes out. I've got wk and x is multiplying my unknown, so I've got to bring that out. And of course, because I'm transposing everything, I have to flip the matrices. And then, so it's this matrix times, of course, what's inside to the power 1, same as before. All right, let's do a little bit of algebra now. I've got 2 times x transpose times WK transpose times WK. So I'm going to go ahead and just square that matrix here. So again, slightly cumbersome notation because I've got a subscript. So all that means is that the diagonal elements on that matrix get squared. There's my unknown M. And then I've got the W out here is going to multiply the W here. So I've got the W squared as well. This term here does not depend on M. This term does depend on M. The 2 is going to drop out when we set equal to 0. This term comes over to the right-hand side. I invert that matrix, and I have my weighted least squares. X transpose, weighting matrix squared, X quantity inverse, X transpose, weighting matrix squared, Y. The K, of course, is because that weighting matrix now depends on the kth model. So do this twice. You get a weighted least squares estimate of this line, and you get a weighted least squares estimate of the second line. And now we've got the pieces for EM. In the E step, we compute the residual, we compute the probability of belonging to each model, assuming we've got some initial estimate of the model parameters. In the M step, we use weighted least squares to re-estimate the model parameters using the probabilities. And then we, as with k-means, repeat until we hit convergence. And what does convergence look like? Basically means that the model parameters are not changing, or they're changing very, very little. Now, that's the basics of the EM algorithm, and there's some implementation details that we need to discuss about. So when we come back, we'll talk about some implementation details that are really important to making sure that you don't get stuck in local minimum and the convergence, that these algorithms converge and they converge to the types of answers that you want.